All right, recording is rolling. It's Monday, April 3rd. So we're going to finish this activity from back on Friday. We were about halfway through. You guys know um, that tomorrow you're going to have a quiz on this simple harmonic motion. Right, so stuff we've been reviewing last few days and today. Also pull out a pendulum FRQ we'll go over today. I always hate to miss school, but tomorrow you guys can have a substitute. That's the way it is. So substitute quiz. Yeah, you go. Okay, and then you guys know after harmonic motion, which is Unit 6 by AP's book, there's just one unit left we have to review, which is rotational dynamics. So I'll throw an extra page at you guys that so that if you finish the quiz early tomorrow, which probably some of you guys will, then you can start looking at Unit 7 type material. Right, so any questions so far before we get rolling? All right. Okay, so the setup, actually I drew the setup right here. Right? The setup was, right, there's this mass on the spring. We pulled it down a few centimeters, let it oscillate up and down. Okay? However far you pull it from the equilibrium position, that'll be the amplitude. We recorded all this data here. Okay? Then we were switching out the masses, treating this sort of like an independent variable, okay? Which is one thing AP likes you to do. They might say like, how stiff is the spring? What's the spring constant? And we approached it two different ways. We went through Hooke's law, right? F versus X, right? Where F is the force. In this case, it was the weight of the mass, right? So as the weight would change, right? The other way was we let it oscillate. We were counting how much time does it take to oscillate, right? Now that one you had to manipulate the axes. So we went with actually it was this right here, 2 pi squared times the mass. If you put that on the vertical axis, and you put time period squared on the horizontal axis, this wasn't perfect, but at least 2 of the 3 points lined up so that the slope would represent the spring constant, which was a match for what we got through Hooke's law version, right? So both ways we got about 19 Newton per meter for how stiff is the spring constant. Right, you guys remember that? Okay. All right, let's look at all the data we have so far. Okay, now I'll give you guys a big old table. Okay, so we're trying different trials, trying different masses. So we went 100 grams, 200 grams, and 500 grams. Here we go. So some of these different lab masses. Ideally, you guys know you would do multiple trials per each one of those. You might do 3 of these, 3 of these, and 3 of these, and like take averages, but save a little bit of time. So what's the time period? Sorry, what's the time to oscillate 10 times? Then divide that by 10 to get time period for one oscillation, so that you can reduce random error, right? Especially with the stopwatch, trying to figure out when to start and stop that. Because if you do 10 divided by 10, that error also gets divided by 10. Okay? So it gets a lot more accurate. Right, we're saying if you hang the each mass on, what's the equilibrium stretch position? Like how far does it stretch from the equilibrium? So with 100 grams, it was 5 centimeters. Double that, each doubles according to Hooke's law. That should be the case, right? Right. Then 500 grams was 26 centimeters. So pretty close on that there. Right? What's the amplitude? So every one of these, I was pulling an additional 2 centimeters to set it into oscillation. So 0.02 meters would be 2 centimeters. Okay. What's the weight in newtons? Well, if you know the mass in grams, you can multiply by either 9.8 or 10 meters per second squared to get the weight in newtons. Okay. So 125 Newton. So this 500 grams is 5 newtons worth of weight, like downforce. We were squaring the time period and then do 2 pi squared times the mass so that we could get these manipulated axes so that we could line everything up. Okay? And that's what we got so far, right? Right? And you guys will be able to come up with that from scratch. Like if AP gave you this exact question, which they pretty well could, you'd be able to do all that so far. Okay? The other thing I wanted to do with this were to create oscillation graphs. So X versus T, V versus T, A versus T. That's the setups on the back. Right, so we got what's the position, say in meters, as a function of time taken away in seconds. Okay? Now this is a lowercase t to represent a variable time, right? Versus the capital T we've been doing so far as like time period, which would be like a set number for mass. I wonder what is the speed in meters per second, or well, let's say velocity because it could go positive or negative. So velocity meters per second, time in seconds. Okay, and then round this out. Let's do acceleration meters per second squared, right, versus time in seconds. Okay, so it's time sigma long. Acceleration. Okay, so you guys probably know what these graphs are going to look like. Right? Right? You guys thinking like sine and cosine type graphs, right? Ones that oscillate back and forth, like sinusoidal. Okay. But let's craft equations and get this exactly. Right? Now, every one of these was a bit different, right? The small mass was like, and then as you make the mass larger, 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 it like slowed down, right? Took more time. So we're going to pick one of these to make an oscillation graph. Let's go with trial 2, the 200-gram lab mass. So this guy right here, which again weighs about 2 newtons, right? Right, so let's do based on that. All right. So I need to bring up an equation for oscillation motion. Okay. And that's going to be, okay, let's use this one right here. Okay. It's about 2/3 way down the page on the AP equations. Okay. It says, here, I'll just copy this here. X equals, fix that. The amplitude times cosine of 2 pi f times t. That's what it says. I hardly ever see AP ask questions about this. Normally, if they do, they ask something like pretty broad. But here, we'll do what we do a lot of times in this class, which is actually like thoroughly go through this, and then like if you understand this fully, then you'll be able to understand anything that AP could throw at you, whatever question I ask. Right now, I think sometimes I write sine here, sine or cosine. You guys know that sine and cosine, if you shift them, they could align exactly, right? So just right. They're just out of phase by I think like 90 degrees or something. I think actually it is a better idea to start with cosine because that shows that like at time 0 there is some displacement so that it could like set it into motion. So it's probably a better way to go about it. Sometimes this 2 pi f you'll see it labeled as omega, which I know in this class omega usually stands for angular velocity. That's not the case in this context. In this context, do you guys know what omega would stand for? It's called angular frequency. And sort of the advantage of taking this whole, because f is just the regular frequency, right? Like 1 over the time period. Okay? So if you multiply by 2 pi, then it will fit nicely into some kind of oscillation equation. Okay? So that when you say what is the velocity as a function of time, okay? If you consolidate all this into one variable, so it sort of helps chunk the information to go from position to velocity. Okay? Now going from position to velocity, that's a rate change with respect to time, right? Okay? Now, I know half of you guys are in calculus, so let's break out some calculus right now. What is the rate change of a cosine function with respect to time? Yeah, sine. And also it's negative, right? Negative. So negative sine. Okay. So rate change of sine is cosine. The rate change of cosine is negative sine. Okay. So we're going to keep the amplitude where it is. So I'll say amplitude. Okay. The rate change of cosine with respect to time becomes a sine graph. Okay. We're going to copy paste all the stuff in here. 2 pi times the frequency times the amount of time it's taken away, right? And then there's one more thing you have to do, which is what? Apply by the derivative of the integral function. Boom. Chain rule. You guys remember chain rule? Well, half of you guys know what I'm talking about. Chain rule. Okay. So yeah, right. All the stuff in parentheses, take the rate change of that, the derivative of that, which is just this part, 2 pi f. Right. Multiply that out here. It's 2 pi f. Which again, if you chunk that as a single variable, it would just you could just write that. So if you see that. Okay. Yeah. So this is the chain rule. Okay. So I'm going to do one more thing here. I'm going to just shuffle this out front. So I'll say that the speed is equal to the amplitude times 2 pi times the frequency. Now, frequency, of course, basically a constant value, right, per mass, right? If there's one mass, there's one time period, and there's one frequency. So that okay. Times sine of 2 pi frequency times the amount of time going by, right? So this t time is still variable. Oh, yeah. Would we apply the negative sign? Oh, yeah. Sorry. Oops. Thank you. Good catch. Negative. So I got a negative right here, right? Maybe I'll just bring it out in front. Make it negative. Yeah. Good call. Negative. Right. And then, like I said, here's going to be position. Here's like the cleanup version of velocity. Acceleration as a function of time. do A of t. Right? So you guys just told me the rate change of sign is cosine. Right? Since there's a negative sign there already, that's just going to stay the same. Okay? So go negative A 2 pi f at a cosine of 2 pi f times t. Okay? And then what's the last thing I have to do?
Multiply by the derivative of the interior function.
There you go. Multiply. Yeah. I like that word in. Multiply by the derivative of the interior function, which is this right here, 2 pi f. Okay. The rate change of 2 pi ft is 2 pi f. Okay. I could just take care of that right here. Boom. Right? Right? That right? All right. So let's graph those two equations right there. Boom, boom, boom. Right. We can do this. All right. Now, take care of this amplitude bit first, right? Because a sine or a cosine graph can go as high or as low as what?
1.
Yeah, 1 to -1, right? So like whatever you plug in for t, this whole bit will max out at 1 and minimize at -1. It'll just oscillate between those two. Let's multiply by the amplitude. The amplitude was 2 centimeters in my case, or what we did back on Friday. Right, so let's go 0.02 negative 0.02, or if you want with centimeters, like 2 and -2. Okay, so we got. So it's like oscillate between those two. The other thing we got to do is, how about time period? So who can tell me what is the time period for what we're working with?
0.64 seconds.
Yeah, 0.64 seconds. Okay. So that means every 0.64 seconds. So 0.64 the 1.28, and so right, it's going to oscillate. Okay. So one complete oscillation, that would look like, here, break this into orders here. Go up here. That would be one oscillation in that time period, wouldn't it? Like that. And then it's just going to repeat from there. And, okay, so there's 2 oscillations. Let's come up with an equation for that. So x as a function of time equals, right? Let's do, all right, I messed up. Right, guys, what's wrong with yeah, initial displacement. I just drew a sine curve. Oops, I meant to do cosine. Right, let me go correct myself here. Let's do peaking. Right. So all I have to do, I mean, it's just shift this thing over, right? So yeah, let's make this a cosine instead of a sine graph. It's just gonna go like this, right? Cosine graph. So get rid of what I initially wrote. Forget that. Exists. All right, so you just care about the pink one, right? Pink one. Yeah. Yeah, I know. On the poster up there, I did write sine. You could do sine or it depends, like when you start the clock, right? So like if I started the clock like right here, it would just be a sine graph. Yeah. Right. So they're the same shape, but you can see them like side by side. They're just one's a shifted version of the other. Right. Yeah. So you could describe it as a sine curve. But, so let's go 0.02. This would be meters. Right, times. Yeah, let's go ahead and make this guy a cosine. Right. And then 2 pi f. Let's go ahead and consolidate that onto one variable. I gave you guys some extra columns here. So let's go omega equals 2 pi f, and this will be in some number of hertz, right? Oh, wait, do I even have regular frequency on here? Oh, we didn't even get that far yet. Oops. Right, let's see it. Frequency in hertz. Okay, I got those columns back, but whatever. We'll do frequency in hertz. Okay. Oh, so that's 1 over the time period, right? That you guys know frequency is 1 over the time period. Frequency. So let's do frequency. So So it's 1 over 0.45 seconds. That is 2.22 hertz. 1 over 0.64 seconds is 1.56 hertz. And then 1 over 1.625, 0.62 hertz. Okay. So it looks like the frequency is decreasing as mass increases, which makes sense, right? The more massive, the more inertia, it like slowed way down. So cycles less frequently. All right, so I got my columns backwards. Oops, because you need this first before you get angular frequency. Let's multiply each one of these by 2 pi. 2.22 times 2 pi, it's like 13.9. And now that'd still be hertz, right? Because 2 pi is just a constant. Okay. 1.56, 9.80, and then 3.9. Okay. And so this 9.80 is 2 pi times the regular frequency. Call it angular frequency. So that'd be right here. So 9.8, and that would be hertz multiplied by the amount of time that's passed. There we go. All right. You're there. All right, so that's this one right here. Next one. So we could change cosine to sine. We're going to throw a negative sign. We're also going to multiply this angular frequency by the amplitude. And so let's do all those things. And so this would be the speed as a function of time is equal to, right? So A times omega, the 0.02 times 9.8, that's 0.196. Right? And it's going to be negative. So negative 0.196. That would be meters times hertz. What is that? What is meters times hertz? What is hertz?
Frequency?
Yeah, frequency. It's like cycles per second, like 1 over seconds.
Like this per
Ah, yeah, meters per second, right? Meters per second, which it should be because we're describing a velocity. It's like some meters per second. So the amplitude of the speed or amplitude of velocity versus time has to be velocity units, meters per second. That's what meters times hertz is. And this is times, okay, we got a sine function. I took care of the negative already. That there. Okay. And 9.8 hertz. Angular frequency is 2 pi f. Put that in there. Okay, times the amount of time it's taken away. Right? We should be able to line up these graphs with each other. Let's see. All right. So a negative sign graph. Okay. That's like starts at the origin, like I was doing before. That's going to go upside down. Okay. And then it'll look like this. There. So it's the same timestamps. 0.64 seconds here, 1.28 seconds here. Right. And a really good question you could get out of this is, what is the maximum speed? Okay. Right. Who can tell me what is the maximum speed?
0.96 meters per second.
Yeah, exactly. Yeah, 0.196 meters per second. 0.196 meters per second. 0.196 meters per second. Right. We just figured that out, but that would be a really good question, wouldn't it? Okay. So you take this 200-gram guy, you put it on that spring that we had back on Friday, pull it down, let it oscillate, right? Then pull it down 2 centimeters, I should say, because that matters too, right? If I pulled it more, it would have to, the time period, here, ask guys this, right? What if instead of pulling 2 centimeters on the oscillate, what if I pulled like 5 centimeters? Right? What would happen to the time period? Did the time period change? Let's go back to that time period. What's the time period for an oscillating pendulum?
2 pi times the square root of m over k.
Boom, 2 pi square root m over k. Okay. Does that have anything to do with amplitude? No. All it has to do with is what mass did I attach to it and what spring did I attach, right? That's it. Right? Anything to do with gravity? No, nothing to do with gravity. You can take this to the moon. It's going to work the same. I could change the amplitude. It's going to be the same time period to cycle, right? So that's the same. Right? But would the maximum speed change? And maximum speed would change, right? Because if I pull it further and it oscillates in the same time period, it has to be going like faster through the center, right? That would be consistent with this too. This whole the amplitude times 2 pi f, right? So frequency would be the same because time period is the same. But the amplitude, if that changes, then the maximum speed also changes, right? Okay. Again, you guys know that this sign bit could maximum or minimize at 1 or -1. So whatever the amplitude of the function is also the maximum value, right? Which is like that. So what's the maximum speed of this thing on that spring from Friday? Boom, it's that. It's the amplitude in meters times the angular frequency. Okay, are we good? All right, here, go and highlight this too, just to keep it consistent. So go over there. And acceleration versus time. Right, so acceleration as a function of time is, so we're going to keep the negative because rate change of sine is cosine, and so there's a negative there already, so that's just going to stick around. I think there's, right, we need this whole chain rule bit. So it's 2 pi f, right, it's going to multiply again. So take my 0.196 times another 9.8. Okay. I'm getting 1.92. Okay. Okay, see how I got that? Okay. I already had this amplitude in terms of velocity. And oh, and then you have to multiply it by another angular frequency. So that'll bring you up to there. Is that right? And then I've got times cosine we're back to, and then 9.8 hertz is the angular frequency. That's the 2 pi f, and then times t, right, where t is the variable. And sorry, what unit? What unit right here? Meters per second squared. Boom, meters per second squared. Okay? And from a couple of perspectives, that works. Right? If you start with meters per second, you take a rate change and multiply it by another hertz. Meters per second times hertz, that's meters per second times 1/seconds. Yeah, it's meters per second squared. The other perspective is, well, of course it should be meters per second squared because we're describing an acceleration. So it would be meters per second squared. So, see, 1.92, 1.92, 1.92. Now this is a negative cosine function, so that's going to start down here. Okay. And then, let's see, here, 0.64 seconds, cycles once, and then after 1.28 seconds, it will cycle the second time. Okay. Just like that. You guys good? Some things to notice too. I mean, why are cosine and sine like rate changes of each other? Sometimes there's negative in the mix. Okay? Well, what if you hold your roller like flush to the curve? Okay? Let's start with the position versus time. Okay? Now, position versus time. See how it starts off at just like flat right here, flat right here. It's also flat right here. As wherever the roller is flat, that means zero slope, right? So the rate change would be zero, right? If there's zero slope. And physically what's going on is that it's turning around. So the mass is like hitting a peak and like turning around. So would that correspond to zero velocity? Bing, zero velocity for each one of those. Okay. Oh, and also true for this third one here. Okay. Bing, bing, bing. I see 0, 0, 0. And also, what about down here? Here's zero velocity. Zero velocity. Right? And then what about this slope right here? What does the slope represent? Right? Velocity. And if I specifically pick this point, what kind of velocity?
Velocity.
Exactly, maximum velocity. Maximum velocity, right? Because that's as steep as it gets. Suppose you're like climbing terrain you're going left to right. You got a little guy hiking left to right. Right, it's going right. Okay, so it's really easy to walk where there's hardly any slope, and it's getting harder, harder, harder. And it's the hardest to cross this point because there's maximum slope. It's the maximum slope, but after that, it just gets shallower. It's easier to climb the rest of the way. Oh, and look at that. Bing, maximum velocity. Is that? And then velocity takes acceleration. It's sort of the same story. Okay. Right. How about this? When this when this is bobbing up and down, okay, when it was had maximum displacement, what can you say about the force from the spring? Was that maximum or minimum? Oh, maximum displacement, F equals kx. The more displacement, the more force, right? The more displacement, the more the spring's pulling back, F equals kx, right? And that actually would be a linear relationship, right? Like if I pull this twice as far, spring's gonna pull back twice as much, F equals kx, right? So I'm thinking at the maximum displacement, there better be maximum force. And think to Newton's second law of motion. This thing is accelerating. So F equals ma. Ooh, should maximum force correspond to maximum acceleration? Right? Let's see if it does. Boom, 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 boom. Right? Or you could pick these 2 points. Boom. Right? You guys see that? That correspond? Okay. And what about when this is passing through the equilibrium point? Right, so like right when it's going through the equilibrium, should all the forces balance out? So there should be zero net force. Okay. If there's zero net force, what's the acceleration? Zero. So that's these 4 points where it's going through the center, right? Bing, all 4. Zero net force, zero acceleration. Okay. When it's going through the center. Okay. Right. So when AP asks you guys that, you guys be ready to answer that, right? When this is going through the equilibrium, then there's zero net force at that point. Okay. Any questions on anything we did back Friday, today? You guys good with all this? Right. Here, let's do one last thing. Let's see what, because I do have an extra column here. Let's do V max. V max. So I'll calculate some V max. You guys calculate V max for each one of these. And actually, one of them you have already. Let's put this in meters per second. Meters per second. Oh, looks like let's put my units down here. Hertz, meters per second. All right. So for the 100-gram mass, this guy right here, to figure it out, what was the maximum speed?
0.04 meters per second.
Wait a minute. Did I do something wrong? Let me check
I'm
this.
not sure if I got the right equation.
So here's our framework for velocity, right? Okay. I'll pause this right here. All right, pause.
Would it be 0.279?
Oh yeah, there you go. 0.279 meters per second. That's what I got too. Right. Yeah. So recording's going again. Right. So remember, looking at this here, you guys know sine or cosine of anything, this could maximize at 1. Right. So really, you care about this. And this came from the regular amplitude multiplied by the angular frequency. Right. That's where that came from. Right. Right. So there you go. There you go. All right. So, all right. Yeah, so that's what Elijah got right there, right? Right, so you guys see 2 pi f times the regular amplitude in meters, 0.02, that's meters, right? That's 2 centimeters right there. Right? The frequency is 2.22 hertz. That came from 1 over the time period. Boom, 1 over that. Right, that's what that is. Yeah, so 0.28 okay. Meters per second. All right, this one we got already, but let's do it again. So 2 pi times the frequency in hertz times the amplitude of 0.02 meters. You're doing 0.196 or 0.20 meters per second. And then this guy, let's do 2 pi times this frequency times amplitude of 0.02 meters, 0.07, something like that. Okay. Ah, look, as the mass is getting bigger and bigger, the maximum speed is getting smaller, which should be in line with, I mean, that should make sense, right? Okay, everybody right? Good. All right. This is actually a pretty good question right there. If you could ask you that. All right, let's look at network two. I'll have you guys turn that in right before you walk out of class today.